So this lab is all about writing better code using the .NET framework, using pre-optimized libraries such as the Intel Integrated Performance Primitives, also known as IPP, and understanding performance analysis tools such as the Intel vTune Performance Analyzer. The lab will begin by introducing the client application and talking about how it fits in with the back-end server. Several opportunities for code tuning will be talked about, along with best practices using the .NET framework libraries and techniques. Then we're going to integrate some highly optimized native library code using the Intel IPP libraries. And then we'll use the vTune Performance Analyzer so that we can talk about measuring performance objectively. The first thing we're going to want to do is examine the code as it is now. The Intel CRM client is a typical intranet application. It's used to manage customers and contacts and opportunities. Data is retrieved from a middleware server on demand, and users can query the data, add and update data, and run reports from the client. The server application is a middleware process that connects to the SQL Server database. It's through this process that the Intel CRM client connects to the database. Next, we'll launch the Visual Studio with the CRM solution. The client application is a managed .NET Windows Forms application written in C#. There's a consolidated list view control with tabs for specific information. Let's start the application now so we can take a look at it. This is the main screen. It is a resizable application. It's divided into 4 main tabs in the toolbar along the side. The Home tab is kind of the launching point. It's the home page for your users. You've got your list of some of your contacts. Maybe these are high profile or contacts that need to be followed up on in the next short while. Meetings that are coming up. And then company news portal, calendar, various activities such as running reports and creating new entities. Let's start by performing a search. And we get one search result, their ID and relevant information about them. And it's designed so you can double-click the row and view more details on the user, make changes. Make a test change here. We'll change the title to Senior Manager. And we'll close the user. This is done by double-clicking the tab. And we'll go back to our search. Bring them up again. And we can already see that the change has persisted. There's also some basic report functionality built in already. Take a look at the contacts directory. And this uses the .NET Report Viewer control. Simplistic, could probably use some logos in it, but it's a good starting point. So now that we've seen the basic functionality, let's take a look and see what kind of optimizations that we could make to the application. So in the second exercise, we're going to talk about some different strategies for optimizing code. Good code is a combination of well-written logic, a good use of system resources, choosing the right class libraries, and knowing when to add threading. So we're going to focus on a number of these areas to provide a boost to the CRM client applications. And this same concepts could easily be applied to other applications as well. Most CRM applications have a report generating function. The Intel CRM sample application doesn't have a lot of reports, but the ones that are there will lock up the user interface while they're being generated. The reason why it locks up is that the database query that retrieves the information is invoked on the user interface thread. So if the thread is processing the database query, it's not going to be able to respond to mouse or keyboard events. So the best thing to do is to execute the report generation and review the results from a second thread. There's a couple of options in the .NET framework. Some work better in different situations than others. For things that need to run at set intervals, the system.threading.timer object periodically invokes a given method on a background thread. If something doesn't need to be executed immediately, you can use the system.threading.threadPool object This will let you queue methods to be executed later. And then the background worker control integrates directly into the user interface. It can be dragged on just like a normal control, and it can be used to invoke code to report progress and to indicate results without cross-threading errors. So we're going to use a fourth method, and this is the highest degree of control, although it does come at a slight cost and complexity. We're going to have complete control over the priority, the name, the culture, the execution context. If it's considered a background thread, we're going to create an explicit thread that gives us complete control. The first step is going to be to add an appropriate using statement at the top of the source file. System.threading namespace. Now we'll change the event handler for the reports command so that a new thread will be created to generate the report. So the report form control, this is another user form that's created, and it uses the .NET report viewer control, and it reads from the RDLC data format. That's an XML structure for defining report definitions. This references different data fields, and they're bound at runtime. The data set, the binding source, these are set directly in the report form to use in the data retrieval and binding it all together into the report. So what we're going to do is factor out the code that's in this method so that we can wrap it into a threading call. We'll use the extract method refactor operation. And this will create a whole new method from the code that was in this original method. And notice it automatically replaces the code from the original method with a call to this new method. It's an easy shortcut for moving code around, and it makes sure that you don't make any mistakes with parameters or anything else. So now we're going to change the declaration. We're going to use a thread pool as the first way that we're going to thread this. And in order to invoke a method as a thread pool, it needs to take a single object parameter. And now up in the tool button, click Event Handler. We're not going to call it directly anymore. We're going to queue it up to run. And we're now ready to debug the application and see how that works. The queueUserWorkItem method adds a unit of work to the queue in the thread pool. When a thread's available, the thread will be assigned to perform the method call. The state info parameter is to allow state information to be passed to the queued method. We could use that to pass which report definition, or if we wanted to pass in some other information like a date range or something like that. It provides a great opportunity for that. Now the report viewer control has requirements for the thread upon which it executes. For just viewing a report, it's not that important, but some of the features require the STA, that is the single threaded apartment threading model. So we've generated the report. Let's try the save method, and we'll execute to Excel. As you can see, an exception has been thrown, and it's a very helpful one. It says specifically the current thread must be single thread apartment, STA, made before HOL calls can be made. This states that we need to set our main function to be the STA thread attribute. But as it turns out, we only need to make sure that the thread that invokes this is running in the single threaded apartment. The STA model specifies how many threads can execute in an apartment, and that impacts COM compatibility. Because the file save dialog is implemented using COM interop, this STA model becomes necessary. The thread pool really simplifies your background processing, but it does take away some of your control. You cannot set the threading model on a pooled thread. So to do that, you're going to need to create an explicit thread. The good thing is that still is not going to affect the main application thread. Let's change this so that instead of using a thread pool to queue the user work item, we just create a new thread and do the work on that new thread instead. And when using an explicit thread, we do not have the requirement of passing the state info, which, as you probably noticed, we didn't actually end up using anyway. Now we're using this report thread object. We'll need to declare that. And finally, we'll need to make sure that we only do this once at a time so that we're not spawning off many threads running the report. Not that the framework wouldn't support it, but it just wouldn't be a very good use case for the application. And finally, we'll want to set the thread object to null when it finishes executing. And we're ready to run the application again. And this time when we run the report, we can export it as Excel, and we get the file name as we expect to get. So executing any method on a separate thread is actually pretty simple. Setting the apartment state is not usually necessary. This was just because we were using the file dialog. For most background tasks, especially network or computational operations, the threading model just isn't relevant. So this is a little bit more complicated because of the UI elements. Threaded code generally has some additional complexity because of trying to synchronize between threads, especially though when you're sharing data between the threads. Every scenario is different though, so you want to really understand how threading works, how your application works, and then you can decide how best to utilize that. So we've added threading to the application, but there's still more that we can do to increase the performance a lot. It's not enough just to add threading. We also want to make sure that we're using the best classes and that we've got the best algorithms, but we're just not going to be able to get the optimum performance using managed code alone. So there are times that we're going to need to just drop into native code. That's the unmanaged code, just Win32 code. And that's stuff that's written to target the processor directly, not just the managed runtime. Code that's written with low-level assembly or C or C++ is going to be able to take full advantage of the processor. The thing is, there's differences in processor architecture, and there's different subtle details that can make it challenging implementing sections of code like this. Whether it's 32-bit or 64-bit, its cache sizes, memory alignment, intricacies with multi-core, that makes it pretty complicated for a managed code developer. But you'll still appreciate the code if there's a way you can take advantage of it. So instead of actually needing to implement all of these things by hand, you can actually take advantage of code that was written by Intel software engineers. And by using a highly optimized library of functions called the Intel Integrated Performance Primitives, you'll be able to do all sorts of low-level functions that can do some pretty complex behavior. One of the samples that Intel bundles is a JPEG encoder and decoder. And that's what we're going to look at integrating with this application. Most .NET developers don't necessarily even think about JPEG and just image processing because so much of it's handled automatically by the framework. But there's a lot of work that goes into that. And the code that's already in place is certainly powerful, but it's not going to achieve the same performance as native implementations. So the JPEG sample codec that Intel bundles uses the IPP library, the Intel Integrated Performance Primitives, and wraps the primitive functions in order to expose them to .NET using the pinvoke mechanism. The sample library includes a fully functional application that will load and save JPEG images. And using the sample application, you can do all sorts of things with filters and manipulations. In the CRM application, we'll create a new picture box control using IPP functions. So the main work is done in the encoder and this decoder CS files. They use managed code for the basic opening, reading, and parsing of the files, but then they use the IPP functions to perform heavy lifting, the actual compression and decompression. So the encoder and the decoder source files do most of the work for the opening, the reading, and parsing of the files. But then they rely on the IPP functions to do the actual compression and decompression. So the encoder file contains most of the high-level classes and methods to handle JPEG encoding. And then the high-level JPEG decoding is in the decoder.cs file. And then there's all of these IPP, CC, CH, core, defs. All of these contain the C# code that invokes the native C code. And then JPEG CS and IPP def contain various enumerations and structures. Each of these IPP files declare the function names that are in the underlying DLLs. For instance, if we go to the IP core file, you see a lot of DLL import attributes, and we don't see a lot of code in here. If you're familiar with the pinvoke mechanism, you'll know that what this will actually do is load a DLL, and then the extern keyword states that the actual method is not going to be implemented in this source file. So at runtime, it will load the DLL, then it's going to find the matching function name, but instead of pointing to managed code, it's going to jump to the unmanaged code instead. This live name variable that you see throughout the various DLL import statements is declared up here. The actual name of the DLL for the ippcore.cs class is ippcore-5.1.dll. We could go to ippch and we'll see essentially the same thing, ippch-5.1.dll. The IPP code methods are actually somewhat versioned based on the name of DLL. They are not managed, so the ability of just embedding an assembly manifest and versioning that way is not going to work. So they're actually versioned through naming. And the 5.1 versions have the dash 5.1. If you had multiple versions on your system, you could select them based on that file name. In an application that wanted to make sure it wasn't going to break with an upgrade, this is important to make sure that you are working with the correct version of the DLLs at runtime because it's dynamically linked. So the Intel picturebox.cs is a visual component. There's no visual designer to look at, it's simply extending the picture box. You can see there's some methods and objects that are declared in order to assist with the JPEG decoding. First thing we're going to need to do is to add a constructor. And I've already got code prepared for that. So the first thing it's going to do is the typical component initialization. It's going to create an underlying bitmap object, adjust the drawing size based on the size of the component, which I won't know until runtime, of course, and then create a destination bitmap object that's used internally. The using block adds system.io and the drawing.imaging namespaces in order to perform the file read and write and the imaging related functions. The IPP and the example IP namespaces are how we import the IPP wrapper methods. So the next thing we need to do is to add a method to open an image from a file. So we'll add that after the constructor. The load JPEG method, we'll read it into a byte array so that they can then be handed to an overloaded load JPEG file method, which works simply with a byte array. So this method is going to call openJPEG, and that's going to do the actual work of the decompression of the JPEG. It's a byte array once we get to this method, whether we first came from a file name or came directly from a byte array. We're going to declare openJPEG in a moment. We haven't added that yet, but it's going to read the headers, it's going to decompress the actual data, it's going to return that then as a bitmap object so that that can then be saved, set aside, and the drawing surface can be adjusted, and then we call invalidate in order to force the surface to redraw itself. So the openJPEG method has a considerable amount of logic in it. First thing it does is it creates a JPEG decoder object, and this is what's going to perform all of the actual work behind the scenes. We set its source to the underlying JPEG itself. We read the header in order to determine color sampling, how many bits per pixel, that sort of thing. And then we have a big switch block. We have a big switch block then that's going to set the underlying bitmap object to the correct parameters. Its pixel format, and then it's what type of color encoding is being used. And then we use the decoder to actually reconstruct the raw image data from the compressed stream. And we set it into the destination bitmap object. and then we can return that as a bitmap. Now, this is an awful lot more code going on here than using the typical bitmap functions in the .NET framework. And so maybe it's counterintuitive that it's going to perform better, but the standard .NET functions do a lot of work behind the scenes. So even though the code is longer, that doesn't have any bearing necessarily on how efficient it is. And of course, the built-in code is going to do a lot more work behind the scenes. So the fact that this is longer code doesn't imply anything for performance. So now what we need to do is rebuild the solution. And we'll need to do this because this is a custom control. We're going to want it to show up in the toolbox so we can actually use it. Build succeeded. So now we can go over to the custom review control. It's another user control. This is where we laid out all of the fields to actually show a customer from the database. Now if we look in the toolbox, under the Intel CRM components, we now have the Intel picture box. We can drag this over. Snap lines make it nice and easy to align it with other objects here. And match it up, basically square. And then just to be sure, we'll want to view the properties. And we can set its size so that it's a perfect square. Close. And then we'll switch over to the events view. And we'll add an event handler for the mouse double-click event. We want to make it really easy for someone to be able to associate an image file with one of the customers in the database. So we'll make it really easy to be able to double-click on the picture control, browse to a file, and make that association. So let's paste in some code that's ready to go. So when somebody double-clicks on the picture box, it's a little bit tricky looking. We're going to create a new thread. We're going to set its apartment state. We did that earlier when we were doing the reports. Start it and join it. And join says that we're going to start this thread and then we're going to wait for it to exit. When the thread exits, we're going to check the file name field and then load the JPEG file as specified in the file name. We're going to serialize that image to a string and then update the current row's photo binary field with this image string. Makes it really easy to send it via the web service back to the database. If there's any error, of course, we'll show a message box. And let's implement the request file name method, which is what the thread is going to invoke. So this creates an open file dialog object. This is a standard file requester from the system. We're going to take the application startup path, add the import directory. That's a folder that we created in the solution that has some images in it already. The filter on the open dialog is going to be based on JPEG extensions. It's just going to show the dialog, wait for it to be clicked OK. Either set the file name to what was selected or set it to null. That's the only thing that this method does. It doesn't return its value anywhere, it simply updates the variable. So how does the other method know when this is done? Well, remember it was invoked on another thread, and then we joined on it. So as soon as it exited, this line exits and it goes to the next line where it's able to check the status of the photo file name. And we still need to place a definition for the photo file name object, so we're going to scroll back up to the top to do that. And we'll declare it right under the current row that we're working on. And then in the constructor, we've got read any attached sound sample and read any attached photo, which has no implementation. We'll add that implementation, which simply says that if the photo binary field is not null, then we want to display it. So keep in mind that the photo binary as it's saved is in a string encoded version of the binary information. Display the raw image. We're going to take that base 64 encoded string, which is the photo binary, and convert it back to a byte array. that the picture box can then work with. We're now ready to debug the solution. Go up to the Search tab, and for our query, search on Doe, contacts, and go. And here's our John Doe. And let's give him a different picture. Double click the field as we defined and go to the import folder. We specify the filter, so there's JPEG images. I'm going to attach the email photo. Now ready to close it. Search again. And he's still in place. So as you can see, we were able to use the IPP routines to encode and decode the JPEG applications. Maybe this wouldn't be worthwhile in a typical client application, but if you're doing any kind of number of transformations, if you're processing a number of images, the efficiency that you gain is more than worth the additional effort that goes into that. Everyone knows it's important to optimize code, but it can be kind of hard to do it well. In a lot of projects, once the code is written, the only changes that are made are basic user interface changes, adding new features, maybe some new business logic, but performance problems are not generally addressed quite as well. Users are complaining it's going slow, it's a pretty subjective kind of thing. Sometimes it may be caused by other tiers that may not even be part of the application, so it can be kind of hard to troubleshoot exactly what work needs to be done. So what we really want to be able to do is objectively measure the performance before and after any optimizations that we make. That way we'll know that we've got the best results and that we're really satisfying the users. So the Intel vTune product is a performance analyzer that can actually monitor the code, take samplings of it as it's running, and chart out the results, make suggestions. It can make sure that you're truly seeing objective information and not just working based on what the users are perceiving as the performance. From the Easy Start dialog, we're going to start a new project. There's a number of types of projects you can create. Notice for each one, there's helpful information on the side to explain what you're doing. We're going to make a call graph wizard that profiles the application. It'll show critical functions and call sequences, give us quite a wealth of information. We'll be able to see just exactly how the application, what calls what as it's running. This is a .NET project. We're specifically going to specify .NET. If we were to specify Windows or Linux profiling, it would be giving us a very different view of the code that's running, and it wouldn't be all that helpful. By choosing .NET profiling, it will be able to go into the assemblies and actually determine what managed methods are being called. We'll need to tell it what application we're going to be monitoring. Location where the exe is created. Double click it. It's going to set the working directory to the same place. This could be useful for locating other modules that it's going to need to run. Call graph data can go into native modules if you want to get a really comprehensive view of what's happening. We could go there if we wanted to view the performance information for the IPP methods. For this exercise, we're not going to do that. We're simply going to look at the .NET methods themselves. When we click Finish, the application's going to launch. It will take a few moments for it to prepare everything, and then it will start sampling data. We're not actually going to go through any methods. We're going to do a pretty simple analysis at this point. Recall that when the application launches, if you can think back, the first screen, the home page of it shows a list of users. It's already connected to the database at the point that the application appears on the screen. So to begin with, let's say the users are complaining that this initialization takes too long. The application should start up a little snappier. So let's see what we can do. Let's see what the call graph information looks like and the performance sampling looks like just for loading in the users. It's appeared. We've got the users there. So that means we've successfully connected to the middleware. We don't really need to do anything else for this analysis. So let's just close the application. So once the data collection is finished, it needs to update its call graph database, process all of that data, and then load it for viewing. It does take a few moments. We'll close the output pane. That's going to make it easier, get a bigger view of the information. We can bring that back by going to the view output. We'll close it again. It's pretty small nodes on here, so I think that's about the best we can do in this view. Let's collapse the various modules to start with. You can see it's profiled information in a variety of .NET base class library and our own Intel CRM.exe. So let's just see the results from here for now. The module, the thread, the function columns, they let you see the library or where they which executable the data was derived from, which execution it was on, and then the specific function that was called. All of the columns, in case you're not sure what a given column is just from the name, all you need to do is right-click on it and simply ask it, what's this column? And the performance environment help comes up. This is the module column. Recall that's the one we right-clicked on. It displays the module name or the Java package to which the function belongs. For COM interface methods, the module column shows the word COM. See the class column for the method name. So if we've not very familiar with all of the functions available in V2, and this is a great benefit. Instead of having to crack open the manual and try to locate some of this information, that single click to get right there can be extremely helpful to save some time to get just the information you need. So we're going to find the main method in the function column, and it's alphabetical. There's the main method. We're going to double click it. And we can see it's highlighted here. You can see that it calls these two methods, that each of these methods call various methods. This one exit out here, this one continues on. You can just faintly read system.windows.forms, so it's doing some visual UI type things. And it's a great way of tracing what exactly is happening at runtime. Right now it's grouping everything by thread. If we uncheck that, it'll bring the entire list down simply to be alphabetized by function. We don't really need to know that. We could still scroll over if we wanted to see the thread, but it's no longer going to group it. Notice right now it's grouping by module name. It was also grouping by thread, and that's not necessary for what we're doing here. If we click the call list tab, it gives the same information, but instead of it being the visual view, flowchart style view, we just get to see the list of the various methods now. So by clicking on any method, it makes it easy to see its caller and any methods that it calls, and then the relative contribution of each of those methods and how much time is spent invoking those methods. Let's click the self time column twice. And this is going to alphabetize the list, first from bottom to top. Now we're going to sort it again so that we can see it from high on top to low on the bottom. And let's find the function convert results to rows. The order of the functions is going to vary probably each time you run it, so it's kind of hard to know exactly what you're going to see there. It's going to depend on the system and what else is running. Of course, in this case, we're retrieving data remotely, and so latency is going to play a role. And then serializing, deserializing. Make sure you're in the right module. Okay, so recall that we are sorted by self-time. Let's just see what exactly it's defined as. This column shows the time in microseconds spent inside a function, including the function's self-wait time. Self-time does not include the time spent in calls to other instrumented functions. So if function A is running and calls function B, the time spent in function B will not count. It's only the time spent doing work inside of function A in that example. So go down a few methods here. We see a number of constructors that performed a lot of work. But convert results to rows. It's called by retrieve all contacts. And then within convert results to rows, we see there's a number of methods being called. Once again, we can sort. We'll click twice so we can see the top numbers at top. And add customers row and set contact ID is where most of the time is spent. We've got a little bit over 12 million for edge time. And we've got just about 5 plus just over 7. So that is about 98% of our edge time spent right there. So this tells us that if we want to bring down the numbers for convert results to rows, we need to start with add customers row and set contact ID. So the vTune Performance Analyzer gives us a lot of insight into how the process is executing, how it affects the processor, its resource utilization. This information can be pretty tedious without the right analysis tools, if it's really possible at all. But now we have a good idea of where we want to start looking at the code. So let's go to the data tier folder and the remote proxy object. And we want to go down to the convert results to rows method. So this method takes an array of data the table itself where we want the data, and then an array that's what comes from the XML RPC service, the web service. It then goes through each line, converts it to a string, it splits it based on the tab character, and then it creates a new customer row. And then it sets the contact ID. When you call add customers row, it doesn't allow you to set the row ID, the primary key itself specifically, and so we end up with 2 calls here. We're also setting the contact ID property separately and invoking the int32.parse method. So let's change this. We're going to explicitly create a new row. Instead of add customers row, we're going to make a new row, and that's returned here, and it's currently empty. There's nothing in that at all. We want to replace the add customers row call and just create a new object array, except we want it to hold the entire object. We want to set all of the columns at once. So we set it to call as 0. And now we've just set it directly. We don't actually need to have a separate explicit call here. So we can delete the call to set the contact ID and the int32.parse. Because this is an object array, we have no trouble setting this as a string, and if necessary we can let the framework manage the conversion of that internally, but that's no longer our concern. We can take that out of our code. And then the last step, this is now an array initialization, which we started with an open brace. We want to also close it with an open brace. And once we've created the row and set the data to it, we'll want to add it. We add it to the database. And we're ready to build the solution. We're not going to actually debug it from here because we want vTune to run it so that it can instrument it. It can profile. So we're going to switch back to the vTune environment. And the activity, this is what we defined within vTune. Each operation that you tell it to do an analysis that's referred to an activity. You've created an activity. Each project could have multiple activities. Each activity can then have multiple results, and then the results are split into the various numbers. We'll collapse this one down. This open pane here is this call graph results right here. So let's say to run the activity again, it's going to perform the exact same steps it did last time. Opens up the output window. And once again, we'll need to wait as it brings up the application. And we're going to do the exact same test as last time. This is the objective. It's repeatable. We don't want it to be hindered by any subjective performance claims. We want to know based on numbers, is it any better? Application has come up. That means it's read the data And once again, we're ready to close it. It can now assemble its information, update its internal information, and load the information into the visual grid. Once again, let's maximize our screen space. Going to collapse all of the modules, locate Intel CRM, and simply open that one. And let's sort it on the self-time again. Once again, we'll need to click it twice. Now we have the biggest ones on top. We can scroll up to the top and find convert results to rows in the function column. When we double click it, and we'll convert to call list again. We can see that the edge time on this method was about 7.5 million microseconds. Let's switch back to the previous results. I took it down from 12 million. Now, that's a pretty big drop. That's about 40% or so drop from the previous execution. I think it's pretty clear that we performed a good optimization there. If we were to use vTune extensively, we could start drilling into other methods and really start seeing other places that we could make optimizations. These optimizations add up very quickly, but most importantly, it will be based on objective, measurable information. No perceptions here, just numbers. We know that we made a change and there was performance increase. The amount of increase that we just made right now would not be perceptibly measurable. We would look at that and say, well, maybe we didn't make any effect, let's revert that back. But throughout the course of the day, that if that method's called many times, if it happens every time they click a certain button in the application to perform a certain operation, it's going to add up very quickly. And by doing that and doing a variety of other enhancements throughout the application, we can be assured that we are definitely improving performance across the board. Writing good code is definitely a great accomplishment. Making it bug-free takes a lot of work. It's not easy, but making it high performance is an even bigger challenge. So you'll want to know that you're using the best framework features and the best third-party libraries. You want to make sure that you make good code that doesn't just run well, but runs responsively and efficiently. IPP primitives give you good low-level raw performance. You can use them in C and C++, and Java and .NET. But to really make sure you're getting to the heart of your performance issues, you want to make sure you're doing performance tuning, that you're running it objectively. Don't just put print lines into your code and put timings in there, but really be able to dig into it with a tool like vTune, where you can take any function, really zoom into it, see exactly what constituents are taking up time. And then when you make changes, you can definitely see without question that you've reduced those numbers and you've improved your performance. There's trial versions of all of these available, IPP and vTune, on the Intel website. So download them, give them a try, and see what you can do with your own code.